Hello, my name is Man Jae-her, and I am a graduate student at DGIST. Today, I'll talk about fully tunable Sagnac loop reflector with 0.1 microwatt static power silicon photonic MEMS. Tunable reflectors in photonic integrated circuit is one of the crucial building blocks in various integrated optical devices. For example, Fabry-Perot interferometers, optical cavities, or pass filters. This can be implemented with tunable fashion using the tunable reflectors. Periodic Bragg gratings are one of the most widely used reflectors in the integrated photonics platform. However, they require complex designs with sub-wavelength scale, feature size, and typically rely on thermal effects for tunability. As an alternative to Bragg gratings, a Sagnac loop mirror is proposed. The Sagnac loop mirror consists of one 3dB coupler with two ports connected in a loop. It is possible to tune the reflectivity and transmittivity by changing the coupling ratio. Tunable Sagnac loop mirror is implemented using thermally tuned MGI. However, large power consumption in milliwatt scale is required, and thermal crosstalk that affect laser performance may occur. From here on, I will show you our way to implement Sagnac loop mirror using MEMS actuators and waveguide. We propose a Sagnac loop reflector that consumes much less power using an electrostatic MEMS actuator, which hardly generates heat. Left figure shows a microscopic image of Sagnac loop reflector. Our Sagnac loop reflector consists of a MEMS tunable directional coupler instead of 3dB couplers. The coupling ratio can be controlled using this coupler. The figure shows the microscopic image of the MEMS tunable coupler. The right figure shows the SEM image of the MEMS tunable coupler. As shown in the figure below, there are two waveguides located in parallel. One of the waveguides is attached to a MEMS actuator. The particular location of the attached waveguide is controlled by the actuator. The right figure shows the simulated response of the tunable coupler with various vertical offset. As shown in the graph, full coupling tuning from 0 to 100% can be achieved by moving the waveguide 1 micron only. For this design, we have about 120 micron long waveguides, and the width of the waveguide is 450 nanometer. This slide shows detail of the working mechanism of our MEMS actuator. We utilize electrostatic cantilever type actuator, which is shown in the left figure. The cantilever is initially lifted about 1 micron. The cantilever is brought down by the electrostatic force between move-up and fixed comb when voltage is applied. From here on, I will show you some measured data. First, we characterize single Sagnac loop reflector. The schematic of the device is located on the left. The right figure shows the measured optical response with voltage applied to the tunable coupler. As shown in the graph, extinction of the transmittivity and reflectivity are as large as 38 and 20 dB respectively. By dividing light into 50-50 ratio, 100% reflectivity is achieved. Next, we built a Fabry-Perot cavity with two Sagnac loop reflectors. You can see the microscopic image and schematic of the device on the left. There are two MEMS tunable directional couplers. The other figure shows the measured spectral response. As shown in the graph, we can find that the line width of the transmission is controlled accurately according to the voltage, which controls the reflectivity of Sagnac loop reflector. When the voltage changes from 13.58 voltage to 13.78 voltage, the line width of the transmission changes from 0.083 nanometer to 0.066 nanometer. The left graph in this slide shows measured current response of the electrostatic MEMS actuator in response to the applied step voltage. The right graph shows the power consumption of the MEMS actuators. This graph is obtained by multiplying the voltage and current in the left graph. The graph indicated that the steady state power consumption is less than 25 nanowatts. We actually expect that the steady state power consumption is much less than 25 nanowatts, as our measurement was limited by the minimum measurable current of our current meter. The reconfiguration energy was calculated by integrating the area below the graph on the right. And our next step is to add phase shifter to our Sagnac loop reflector marked in the figure. FSR can be tuned by changing the cavity length using the phase shifter. Several MEMS phase shifters have been demonstrated so far, and some of them has footprints less than 100 micron by 100 micron. So we should be able to pack them into the empty area. These are the most recent demonstrations on MEMS phase shifter, including the one from our group. The process flows are pretty much similar to the Sagnac loop reflector, so integrating MEMS phase shifter should not be a large issue. This is a summary of my talk. So far, we have experimentally demonstrated fully tunable Sagnac loop reflector using silicon photonic MEMS technology. Our device consumes power on a nanowatt scale. Our next step is to add phase shifter to our device to have a completely set of tuning. This work has been done by collaboration with Professor Kyung-Sik Yu at DGIST. This work is supported by Samsung Science and Technology Foundation and Daegu Gyeongbuk Institute of Science and Technology in Korea. Thank you for listening.